with, I feel honored to be able to present at this particular session. So I'd like to speak to you this morning about automated model checking, and in particular about more complex code requirements. We heard a very inspiring talk yesterday from Nick Nisbet of EC3 in the Industry Day, which concerned another system, a very pioneering system, I think, for code checking, where one can take not only codes, but requirements that expressed in text of different kinds, and express them using just 4 colors, and then check for the requirements. But the challenge with that, and with all the existing code checking software that is out there, is that we require that the information be in very specific forms. And unfortunately, often it is the case that that information is not available in the ways that we wish. And that's the reason that we have to deal with much more complex requirements and much more complex relationships between the information available and the information needed. And that's what this is really all about. So when I talk about the motivation, we're really talking about the need for what we have termed semantic enrichment. And semantic enrichment can be done with rule inferencing, with machine learning, with other AI techniques. But the real goals of that are to take building models in whatever format we receive them. And by format, I mean, in this case, both the syntax and the semantics of the model, and convert them as automatically as possible into formats that can be read and can be evaluated with the simple tools or the straightforward tools that exist. So our research goals in this case were to look at particularly complex code requirements, complex in terms of the topology of the objects in the models, and to figure out how we can do that, how we can bring them to a stage where they can be simply evaluated. I had the privilege to work for a number of years and to some extent continue to work with Chuck Eastman. Chuck wrote a paper in 1975 where he spoke about the future of building information modeling. Of course, it was not called that until 2001, 2002. And although systems did exist, but he envisaged all of these different things. And in reading this through, you will recognize that many of these things have become reality 45 years later. Now, you need to imagine what computing was like in 1975. And I want to pick up particularly on this. In fact, when you read this paper from the AIA journal, you realize that one can conceive of a BDS, building design system, supporting automated building code checking is perhaps the only prediction that Chuck made at that time that is not yet common practice. And to some extent, this sits behind a lot of what we're doing, this challenge that of all the different benefits that we expect industry to reap from BIM, this is perhaps what's still lacking. So what are the questions? Today's model checking applications are capable of checking building models for conformance to clauses, but they are restricted to fairly explicit dimensional values and some slightly more linguistic values rather than numerical values, but basically you have to spell it out. Why is that? Why can we not deal with more complex things? The complex implicit code clauses are still beyond the scope. The reason for that is that software cannot read building models in the way that any of you can. When any of you look at a model, you see in that model much more than is explicitly recorded in the computer record. So we suggest, and we've suggested this for some years, that much R&D is needed for semantic enrichment to pre-process models for checking, the idea being to make the implicit information explicit. And the paper I'm presenting is an effort in that direction, one of many. So we know that the most common schema, the most common syntax for presenting models nowadays is the IFC. It has become the de facto industry standard as it was intended. There are many people who do not use it because they're entirely locked into one or other company or vendor's software, But in the large part, this really is a very useful representation. And we also know that code checking requires higher levels of semantic information. In fact, I don't have a slide that shows this, but you could think of it this way. We know that we had CAD. We know that CAD represented objects as lines, arcs, and so on as symbolic representation. Above CAD, we have BIM, which in our minds, for the last 15, 20 years, we've imagined that, yes, and many of us have written, and I include myself as guilty in this, BIM will provide all the information that's computer readable. It will be able to be checked by systems. But no, it turns out that we need a higher level. We need a higher level than BIM, which will, in this case, we believe, be provided by AI and BIM. So this is the challenge. Most of the systems that we have require this manual pre-processing stage called normalization, where I take a model, I either prescribe to the architects, engineers, builders, designers, what must be in that model and in what format. I do that using the information delivery manual, the model view definition, contracts, LOD specifications, a range of things where I can specify precisely the information requirements I need so that models can be used for, amongst other applications, code checking. And semantic enrichment is intended to come along and say, can we supplement those basic definitions and perhaps even reach a point where we can take any model, even basic geometry, and as a human being would look at it, not the average human being, an engineer, professional, would look at it and recognize objects, software can too. So let's look at it in more detail. So we have in building models, of course, we have geometry, and we also have some semantics about that geometry, what it means. And when they're exported, much of those semantic information remains implicit. It could be because the information was never entered, for example, a definition of a space as a room amongst four walls, but it can also be that the export routines themselves are deficient, and they're not exporting everything that's in the model. And it doesn't really matter whether it's because the information was missing to begin with or because it was not exported correctly. Either way, the model we get is not sufficient for our needs. And specifically, we're talking here about parameters, aggregations of things, connections between things, and other topological structures between the elements in the model. So what are we looking at? What is that? What kind of building? This is a question, it's a conversation. So. Residential, it's an apartment. How do you know? From the plan. Now, I assume that you recognize that that's a balcony, and that's the entrance, and perhaps this is the kitchen, right? And you have the idea that this might be a bedroom. None of that information is in that model. None of that is written in. The BIM model contains the walls, the doors, the windows, etc. But the fact that it's an apartment and it has a bedroom and a bathroom and a balcony and so on is entirely something that you have read into that by the fact that you recognize that plan. And by the way, it's a CAD representation in 2D. It's not even a BIM model. And yet we all understand that very immediately. And so that's really what we're talking about, to recognize those things. For example, here, we recognize that there is direct access between that bathroom and that bedroom, which to us screams out master bedroom, parents' bedroom, or something like that. Yeah? But there's nothing of that in the model. So if we think about this whole process of code checking, really what we're talking about here is we have a model checking process where we want to take an IFC file, a model, we want to normalize it in some way, and then we can do some rule processing using predicate logic, as we heard yesterday, and then get some results. But what we really have to do in the background is take the building code, recognize the concepts that we need, the bedroom, the bathroom, the balcony, and whatever else, and then we have to compile the rules. We then get the rule sets, and we get the rule processing. And most of the existing systems, whether they be Solibri or the system that we were presented yesterday, which seems to be a step ahead by EC3. I apologize, Nick, I don't remember the name. Require one. they all require these processes, but this process is something that currently we require architects, designers, engineers to do themselves, and we have to have some discipline for them to do it. Why should they do it? Well, presumably because somebody's paying for them to do it, and we need that to be done, otherwise we can't do this code checking. In the way that the construction industry is set up and so distributed and so many different responsibilities, this becomes a big problem. So what we propose is a two-layer operation. We have this process going from a model to results of code checking, which requires a semantic enrichment, and then a code checking process. These things are fairly well understood, but this is the core, the heart of our problem. We have another layer running below it, which you saw in the previous slide, where we take the building code, we define the concepts or the information objects that we need. Those are the ones that have to be enriched, but those are also the ones that enable us to get to the results. And if we divide this up, we see that if I use this, not imprecise terms for a moment, this is done offline, or I should say in the background. This is done online, so to speak, every day by authorities, owners, others who are checking the models. And you can also divide it up here. There is a section here, particularly, which is the semantic enrichment part, and then there's the code compliance checking part, which I won't go into now. It turns out that if you do a lot of this, then this becomes very simple. If you enrich the model to the point where you have everything explicit in the model, then you can do code compliance checking fairly straightforward. There is an alternative, and that is to use more machine learning here in the checking, where you might say then, as you or I could look at that apartment and say, does it meet some particular code requirement? And right away you know the answer. And you know that answer because of your experience and your recognition of patterns. There is a hope that we can do some of the code checking using machine learning here by recognizing patterns without knowing anything about the logic of the code specifications. That's a great target, and people are pursuing it. It's not what I'm talking about here and now. What I'm talking about now is the idea that we can actually enrich the model fully to get to the semantics. So there are different ways of doing this. We can think of it this way. There's the semantic enrichment, there's the code compliance checking. Either can be done with either of these tools, and I recommend that anyone who wants to engage in research in this area, all of these are valid and useful areas to try to make progress. Some of them in the long term or the midterm may turn out to be more fruitful than others, but the jury is still out on that. And you can think of it this way, that we have examples here. Using rule processing, we have good ideas of how to do this. Trouble is, it's a little bit labor intensive. We have existing code compliance checking applications, Celebri, Smart Review, and a number of others. But these are very much the topic of current research. So what are our goals? We want to understand the structure and characteristics of problems, what the problems are like, what their characteristics are. We want to explore a range of test cases for solving them, and the general expected result is a framework for semantic enrichment to support code checking. And in work that I'm not going to present now, we are trying to classify all these various needs for semantic enrichment and then figure out, by clustering them, which approaches on the spectrum between learning and rule processing, inferencing, are appropriate for each particular type. And we hope to report more of that ongoing. But for now, I want to show you an example to make it very specific what we mean by topologically complex code requirements. So we have, in Israel, we have a building code which requires every building to have a security room, meaning a blast-proof shelter, a shelter safe for chemical weapons. And there are two options. You may either have an individual room in each apartment. You may also have a room on the floor of the building, which in itself is secure, and everybody who lives on that floor of the building or works on that floor of the building is able to access at time of need. And in this case, there is a room placed over here which serves the whole the floor of that building. Now, one of the requirements is that at least 70% of the walls of that room must be continuous down through to the foundations of the building. So if we look at the circumference of the room, 70% of that circumference must follow through continuously through, in this case, concrete walls to the foundations. The idea being that it should remain standing even if the rest of the building is damaged. So how do you check this, and how do you meet that requirement? Well, just symbolically, if you think of it this way, if I'm on the 3rd floor and I have a room on the 4th floor with 4 walls, and the walls below me are like this, and then the 2nd floor and the 1st floor and the basement, we ask ourselves how much of those walls follow through. So at this level, of course, the basement is fully supported. On the 1st floor, those 3 walls, 75% of them in this case follow through to the foundations. But here, of course, this wall is missing. This wall does not follow through, leaving us with only these 2. And so on the 3rd floor, that kind of configuration would fail, this code requirement. Now, as a human being, look at that, I need to look through all the drawings, the whole model, all the way from the foundations up to the room I'm considering to be able to make this assessment. But if I want to do it with a building model, I actually have to have the relationships between each of those walls and the wall supporting it, following through down to the foundations, to be able to follow that chain of support in order to make my decision. And so this part, this enriched model, must now include all of those relationships. And in fact, if I want to do the whole hog, I have to actually record in that enriched model for every security room what percentage of its walls follow through to the foundations. Then I can use require 1 to decide whether it passes or fails. So how are we going to do this? The first step is I have to identify those rooms. I need to know which are rooms. After that, I have to identify which are security rooms, because those are the only ones to which this requirement applies. This section we do with machine learning, because, this section is done with rules, but identifying the rules is done, we do commonly now with learning. We've shown that that works quite well. We get relatively high accuracy. Because the learning algorithms report a level of confidence for each conclusion, we're able to have a threshold, not on this number of accuracy, but on the probability of meeting that classification, so that any rooms that don't achieve the threshold are reported back to the supervisor, the human being who's monitoring this, and all the rest are done. So there's a sort of a Pareto solution where the vast majority of the cases are dealt with automatically and the exceptions are dealt with by people. And then we want to associate the walls around the room to that room, and this is just a quick predicate logic, quite a simple solution for doing this, but it's very typical of the kind of rule inferencing-based semantic enrichment that we can do. So we can take a set of rules. These are operated on every pair of elements in a BIM model. And I say elements using the word very carefully, meaning IFC building elements. So every wall, column, door, window, whatever is compared to every other wall, column, door, window in a cyclical fashion until no more new information can be added using forward chaining. And the result is that, we get this association, this aggregation of the walls. The same thing, it's exactly the same rule implemented in the CBIM2 system. And you simply compile these rules, whatever, and you get the logic, and it can upload IFC models and process them and add the information. Andre Bormann and his team in Munich were significant in working with us to compile this tool and in extending it from using bounding boxes and so on to using arbitrary geometry. And Ling Ma, who is with us here today as well, worked on this a great deal at Technion. So 3 minutes, no problem. So really what we're trying to do here is then, in the next step, we want to identify the walls and foundations that follow through. So a wall over here, supported on a slab, supported by a wall, supported on a slab, following through to a wall. You can see that you need to compute now these areas of overlap. And so for that, we have a specific geometry operator implemented in CBIM2 that can take walls which are in contact and create or generate a new object, a topological object called that interface, and install it in the model with pointers to the walls on either side in relationships. And that's what you see here. this, calculating this Ported area and creating the relationships between the objects. And once you do that, you can then get to this point and say, if object 1 is an IFC space and object 1 is a security room, and the walls to foundation ratio, which has been added and supplemented into its information, is greater than 70%, then obviously it passes the clause of the code. So here's a quick example from a building in Tel Aviv. Building has 6 apartments on each floor, 8 floors, underground parking, and so on. And what you see here is this is the security room in the building. This is a typical security room. And in the basement, of course, we don't need such a room, so it's a bicycle parking. But as you see, it has openings here and openings here. And we're now going to check whether that stack of rooms that you see, well, it runs up the building in this way, whether that stack of rooms meets the code. And so we go to CBIM, we open up the right rule set, we upload the model, and we run it. Of course, because we're taking an example of an existing building which has a building permit, it meets all the code. To test our system, we say, let's make some changes to the building and see if we can cause it to fail. So we change the material of one of the walls on the 4th floor from concrete to block, rendering it irrelevant as a concrete wall. And we create an opening on the north wall of the security room, and we see what happens. Then we run. And what you see is when we do a manual check, we simply, to do the manual check, we go to each wall on each floor of the building, and we figure out the percent supported. And you see that once we've removed these things, on the first floors, in the parking, the ground floor, and then as we got the building on the 4th floor, despite having opened up that one wall to be made of blocks, it's still okay. On the 6th floor, with the opening on the basement, we now find that it fails. And now we go to the model and check, and lo and behold, we find that we get the same result, and we have some confidence in that our checking system is working. So that on the 4th floor, it still passes. On the 6th floor, it's now failing. Yeah. So, to conclude, since I guess I have 0 time left. We're able to do this with rule sets. We're able to do it with some aspects of machine learning to supplement. We believe that it's feasible to compose all of these rule sets. The rules progressively add the concepts that are needed. Of course, we have to define what those concepts are in a model view definition ahead of time. We have not found a way to escape that. Selection of rule-based or machine learning depends on the nature of the problem, and as I said, that's the subject of what we're doing these days, and hope to report that. There is also another thread of research that says, can we do the rule checking by collecting hundreds or perhaps thousands of examples of pass or fail cases that we know, label them and use them for learning to predict future cases without any knowledge of the logic behind those rules. And thank you very much.